All right, guys, for lesson 3, we're going to be looking at torque in equilibrium when our forces are not at 90-degree angles. All right, so once again, we've talked a little bit about torque so far, but we've been only talking about it when the forces are acting perpendicular. So we're going to look at what happens when the forces are not perpendicular. For example, we have this problem here on the right. All right, so notice we have a 100 Newton sign that's hanging down. And it's being held up by a uniform beam that is horizontal to the ground, as well as a cord that's attached to the ceiling or attached to, whatever the overhang. And that cord's not straight up and down, right? It is being held at a 30-degree angle. All right. So when we're talking about this, we want to find what's the tension in this rope here. And we also want to find what are the vertical and horizontal components of the supporting force provided by our hinge over here on the left. So remembering that that is also providing a force. All right, so we have a couple things that we want to do here, right? We just kind of want to break this down in a way that's going to make a little more sense and allow us to problem solve this a little more strategically. So a couple things, I'm just going to kind of define this a little bit. So we have our tensional force here, right? Let me just thicken this line a bit. All right, so I'm going to call this T, right? And then notice our uniform beam, we actually have two gravitational forces, right? We have the gravitational force of the 100 Newton mass here. So I'm going to call this FG1. I also have the gravitational force of the beam itself, right? And that's going to pull down from the center of mass. I'm going to call this FG2. Now, I can probably reason here that the tensional force of the rope is probably not the only thing that's going to be holding this whole beam sign system up, right? I can probably reason that this hinge over here, right, which is going to be my pivot point, is going to also be contributing. And I know that it's going to be contributing a force in the y direction and also a force in the x direction, right? Knowing that my sign is being pulled at from an angle. Okay. So kind of analyze my diagram a little bit here. So again, kind of key thing is just knowing that in terms of gravitational force, I have two, one for the sign, one for the beam. So to kind of simplify this a little bit, I'm going to redraw it here and then kind of define some of the distances from my pivot point or the hinge. So I have my beam here. All right, and I have my tensional force. All right, and then I have FG1, FG2, Fy, Fx. All right, so one of the first things I want to do here is I want to break down my tensional force into a couple of different components. All right, because I know, right, with it pulling at an angle, we can break that down into its x and y components. So but here's the key thing, right? So we know it has a y component going up and an x component going this way. But you'll notice I'm not going to label them ty and tx. No, when we're talking about torque, what's going to be more useful to us is labeling them T perpendicular and T parallel. All right, Because what we want to know is we really want to know what forces are going to be perpendicular to the motion of our rotating object and what forces are going to be parallel. Notice that the parallel force really isn't going to have much effect on my uniform beam, right? You think about a door, right? If you pull at the end of a door, right, you're pulling opposite the hinges, the door's not really going to move at all, right? That parallel force doesn't do much. It's a perpendicular force that's going to have much more of the impact, right? That's where all your force is going to be actually causing the motion. All right, so we kind of established that. We broke down our tensional force into its two components, right? Tension perpendicular to the beam and tension parallel. Now we also know with torque that one important component is going to be knowing both force and distance, right? So here we can kind of define our distance from our pivot. We kind of established that our pivot, right, is going to be this hinge here. So in the problem, it's telling us that the entire beam itself is 2.2 meters long. All right, so that's going to be a distance from the pivot to the end, which is where the sign is hanging down from. We also know that from the pivot to the center of mass of the uniform beam itself, the distance is going to be 1.1 meters. All right. So, a couple of things here. We want to notice that if we break our tension, the rope, into component forces, sorry, I kind of mentioned this, but wanted to add it here, right? The parallel force or the parallel component does not contribute to torque, right? Our parallel component is not impacting the torque or the rotation of our object. So whenever we're calculating torque on a body, whether it's a wheel, a uniform beam, etc., we are always going to use the perpendicular component of the force. So here we go. What we're going to do is we're going to go ahead and solve this. So key thing is all these problems, right? All our objects are at equilibrium, right? They're not moving. So this kind of allows us to understand that tau clockwise is going to be equal to tau counterclockwise. Right? So remember, we have two forces. One force that's pulling it in a clockwise motion, one force that's pulling it in a counterclockwise motion, right? So if we're looking at this problem, right, think about a clock, right? Our clockwise motion is going to be defined as our combined gravitational forces, right? So remember that tau is equal to, so this is just a reminder, tau is equal to FD, force distance. So let's define it here. So our tau clockwise is going to be gravity 1, right? That's the hanging sign, multiplied by distance 1. Say this is D1, this is D2, okay? Plus FG2, D2. Now, these are going to equal the perpendicular force of our tension. Remember, the parallel force does not contribute to the torque, right? So what's contributing to the counterclockwise torque of the sign is the perpendicular force of that tensional rope. All right. So it's perpendicular force, right? And that's going to be D2, right? The force is being applied 2.2 meters from the hinge. This particular problem, right, what we want to find is what is that perpendicular force. Right. So in solving for it, right, we're just dividing both sides by D2. So we get FG1 D1 plus FG2 D2 all divided by D2. We can plug in our numbers. Right, we get 50 newtons. Right, which is our weight of the whole beam itself. and the distance is 1.1. That's going to be plus the weight of the sign, right, which is 100 times the distance, all divided by the total distance. This gives us approximately 125 newtons. Now, keep in mind, 125 newtons is our perpendicular force, but the actual problem itself is asking, what is the tension in the rope? So we haven't actually solved our problem yet, right? I'm just redrawing our rope here. Okay, so we do know the angle here, right? So a couple things that we know. There's a couple different ways we can solve this. Again, this is just kind of our basic trig. Right. So I know my angle here is 30 degrees, which means that my angle here is 60. All right. Now I'm trying to find T, right? What's the tension, the force? So just using basic trig, right? I know that cosine 60 degrees is going to equal my parallel force, or sorry, my perpendicular force over tension, right? Solve for tension. Get a parallel over cosine 60 equals 125 over cosine 60 equals 250 newtons. All right. So we solve for A, right? 250 newtons, which is great. But one thing here, again, we'll notice this in both ways. The tensional force of the rope is 250 newtons. But more importantly, the perpendicular force of that rope is 125 newtons. Whereas we know that the gravitational force pulling down the beam is 50 newtons plus the sign is 100, right? So a total of 150 newtons pulling that sign down. So we can reason that there must be an additional force holding the whole sign system up, provided by the hinge, right? That's the only other place that we could have some force being applied. So let's look from a Y perspective. I'm going to choose a new color. Just a little bit thicker. Okay, so I'm going to look at all my forces in the Y direction, right? This must involve the Y force of the hinge, right? Because my perpendicular force does not equal the combined gravitational forces. So Fy plus T perpendicular, if we subtract those from Fg1 and Fg2, we should get a net force of 0. Now, what I want to do is I want to solve for Fy. That's a P. So I get Fg1 plus Fg2 minus T perpendicular equals 50 plus 100 minus 125 equals 25 newtons. All right. Now it's also asking for vertical and horizontal components. We just found the vertical component of the hinge, right? That is 25 newtons. So 25 plus 125, the perpendicular force, is going to equal our gravitational forces, right? These two here equal 150 newtons, which equals the gravitational force. It's asking us to find what is Fx, right? Now I know, again, the only two x components I have are the x component of the hinge and the perpendicular component of the rope. Right, so this and this. And because this is all in equilibrium, right, my force in the x direction of the hinge is going to be equal to the perpendicular component of the tensional rope. All right. Again, if I want to find the perpendicular component here, I can just go back to kind of my trig here. I know that this is going to be 30-degree angle, right? Solving for t perpendicular, I just end up with t, so the total tension, sine 60 equals 250, sine 60, right? Because we already solved for the tension, the hypotenuse, end up with 217 newtons is our x component. Right. So the y component of the hinge, the x component of the hinge, we have the tensional force. Several steps to kind of get there, but those are our answers for A and B. Okay, moving on. Let's talk about rules when we have torque not at a 90-degree angle. So when we find torque acting on a body, we must always use the component of the force that is perpendicular to the beam. All right, parallel force doesn't really matter so much, right? All right, so we have here 1.8 meter long uniform beam. Is 12 kilograms mass, attached to a wall by a hinge, supported by a rope. A couple things here. We know the angle between the beam and the ground. We're trying to find the tension of the rope. Now keep in mind, even though the rope is vertical, it is at an angle in respect to the uniform beam, right? So don't let that confuse you. So a couple things here for us to kind of make sense of this particular problem. Because our forces are not at a 90-degree angle, right? We are not talking about perpendicular forces. We need to break down these components into a way that's going to make sense to us. So let's start by considering the gravitational force acting on this beam. Remember, we draw our gravitational force from the center of mass. So notice that the gravitational force is already acting at an angle. So we can do here, once again, let's break this down into our components. Everybody do this not in x and y, but in perpendicular and parallel. Okay. All right, so let's consider here, right? This force is our perpendicular. FG perpendicular, FG parallel. Remember, the main one we're focusing on is perpendicular. Again, knowing just our basic geometry, right? If this is a 32-degree angle here, this is also a 32-degree angle being formed. Obviously, right triangle. All right. Now, one other thing we can kind of consider, if our whole beam is 1.8 meters long, then that means that the distance to the pivot, to the center of mass, is going to be 0.9 meters. We'll call this D1, and this can be D2. All right, let's do the same thing for our tensional rope. All right, so we got tension. We have our force that's perpendicular and our force that's parallel. So F perpendicular, F parallel. Keep writing F instead of T, sorry. T perpendicular, T parallel, right? Because these are components of our tensional force. All right, so 90-degree angle. And again, in this case, right, this is just basic geometry. If you need a refresher, I can give you some resources. But again, the angle made here is going to be also 32 degrees. All right. So, broke down this whole problem. And again, our pivot point is this hinge over here. So, our goal is to simply find the tension. Now, we don't really know anything about the tensional force yet. What we do know is we do know the mass of the beam, which means that we can kind of determine the gravitational force components. So let's start with that. All right. So I know that Fg, right, this force down here, right, which is the gravitational force acting on the beam, is equal to my mass of the beam times gravity, right, which is going to be 12 kilograms times 9.8, gives me about 117.6 newtons. Now, since I know what that component is, right, force gravity or the hypotenuse is 117.6 newtons, and I know the angle, I could figure out, right, the perpendicular side or the parallel side. In this case, again, the parallel side is not going to really be a factor in my equations. So, simply here, if I'm trying to find force gravity parallel, so Fg parallel is just going to be equal to the hypotenuse, force gravity, times cosine 32. All right, so I plug in 117.6 for my force of gravity. That's going to give me about 99.73 newtons. All right. So, figured out my perpendicular force, right? 99.73 newtons. Now, I know, as in all of these problems, that my object is in equilibrium, right? Now notice, right, my perpendicular gravitational force is opposite my tensional perpendicular force. And those forces are going to be equal, right? Or I should say the torques are going to be equal. Different forces because they're at different distances from the pivot. So let's go ahead and define it, right? So I have Fg perpendicular, distance 1, right? That's halfway to the pivot. It's going to be equal to T perpendicular D2. And in this particular problem, I am trying to solve for T perpendicular. So T perpendicular is just going to give me Fg perpendicular D1 all over D2. plug in the numbers I know. So 99.73 times 0.9 all over 1.8. T perpendicular is going to give me 49.87. Okay. All right. Now from here, all I need to do is I have one angle and I have one side. I just need to find tension. All right. So again, it's just basic trig. All right. So it's going to be equal to T perpendicular over cosine 32 equal 58.8 newtons. That's it. Now, one thing I want to show you guys real quick is that in a problem like this, there is actually a shortcut. All right, it took us many different steps, right? We had to first figure out what was the component of gravity, break that down into its perpendicular component, match that to the tensional perpendicular component, and then use that to find tension, right, the hypotenuse. There is a shortcut, however, that we can use in a problem that's just like this. All right. In this case, we know initially, and we kind of proved that the perpendicular component of gravity, right, and its distance, so the torque, is going to be equal to the torque provided by the rope. Now, we know that in each of these, we were given that perpendicular force by the angle, right? So we know that we got Fg cosine 32 d1 equals T cosine 32 d2, right? We saw that in both cases. Now we know if we end up with an equation like this, right, we can cancel out cosine 32 or cosine of whatever the angle is. And from there, right, you get to just solve. In this case, we're trying to solve for t, right? You can do the same thing solving for distance or gravity, whatever it is, right? T just becomes Fg d1 over d2. In that case, you don't need to know the individual components. We were able to just skip straight to. However, I do caution you, this shortcut only works when you have the same angles. All right, only works when you have the same angles. Okay. So, final problem here. Oops. I have to add this. All right. So this one, we have a hanging object. The mass of our uniform beam is 115 newtons. It's held at an angle by a rope. It's horizontal. And you have a hanging mass, and we're trying to determine what is the mass of that object. So, again, one thing that's going to be helpful is kind of determining several different pieces. So we want to kind of break down this diagram into components that we can know and define. couple things I'm missing. I also know the tension of this rope is 165 newtons. Sorry. What was it? 675 newtons. All right, that should already be on your paper. So this is what you guys should see right now before doing anything. All right. Couple things I want to do in this particular problem. I want to break down all these different pieces into their individual components. And I have three, right? I have the gravitational force of my beam. I have the gravitational force of the mass here. So I'm going to call this FG1, FG2. I have the tensional force provided by this rope. Right, and that's T. Let's see. Okay. I have the distance. We call this D1, D2. All right, so I have the distance of the whole beam, and I have the distance of half the beam to the center of gravity. All right. Now, what I can do here is I have three different forces, basically, all acting at an angle. FG1, FG2, and the tensional force. I can break these down into their parallel and perpendicular components. All right. So we're going to take a couple minutes to do that. Okay. Make a right triangle here. Right triangle here. Supposed to be a right triangle. All right, and then let me define these. Okay, so I have FG1 perpendicular, FG1 parallel, FG2 parallel, FG2 perpendicular, and then I have tension perpendicular, and tension parallel. Again, the ones we're focused on are our perpendicular forces. Okay. Now, let's consider angles, right? Just doing some basic geometry. So I know that the angle between my tensional rope and the uniform beam is 50 degrees. Which means that this angle here is also going to be 50 degrees. All right. This angle here is going to be 50 degrees as well, which tells me that this angle here is going to be 40 degrees, which is the same thing I'm going to see here. Okay. So I broke down my three different forces into their component pieces. All right. So it looks a little messy. Again, sometimes it's helpful to take all those components and then just draw them out separately. But for the purposes of this, I'm going to just keep going. All right. So again, because it's all in equilibrium, I know that my torques that are counterclockwise are going to be equal to my torques that are clockwise. So let me define that all. Right. I know that I have my clockwise torque, or I guess just one side, is provided by the rope, right? So my torque is going to be the force of that rope perpendicular times the distance to the pivot. Keeping in mind that I don't actually know the distance, but you'll find that we don't actually need to know it. So this is going to be equal to, again, my two gravitational forces. So I have Fg1 perpendicular times distance plus Fg2 perpendicular times 1/2 the distance. Again, I don't know what the actual length of this beam is, but I do know that whatever the length is, the distance from the pivot to the center point is going to be 1/2 that total distance. Okay. Now, a couple things. I already know when I'm looking at this particular problem that if I were to simplify this, right, I could eliminate distance from all pieces of this. All right. Now, kind of what we already looked at. I know that for tension, right, my perpendicular tension force, I know the angle and I know the hypotenuse, right, that was given. Right, the hypotenuse is 675. So if I want to find tension perpendicular, this is going to be, tension cosine 50, which is going to be equal to, where I do kind of the same thing, Fg1 is going to be equal to cosine 40 plus 1/2, right? We got rid of the distance, but didn't get rid of that 1/2. 1/2 Fg2 cosine 40. Okay. And now, in this particular problem, I am solving specifically for the mass of the hanging object. So I'm going to isolate Fg1. And notice I'm doing all this before plugging in any numbers. And this is going to make it a lot simpler, right? At least in my mind. Okay, so Fg1 cosine 50 minus 1/2 Fg2 cosine 40, all divided by cosine 40. Plug in my numbers. All right, tension 675, cosine 50 minus 1/2, 115. Right, it's mass of the beam times cosine 40 all over cosine 40 equals approximately 508.9 newtons. Now keep in mind, the actual problem itself is asking for the mass. Right. So if we're getting our answer in newtons, we know that that is the weight of the hanging object, not the mass. Right? And we know that mass is equal to gravitational force over g, right? Which is going to be equal to, all right, so 508.9 divided by 9.8, we're going to get about 52 kilograms. That is our final answer.